Hello once again, AP Calculus BC students. Mr. Record here from Avon High School in Avon, Indiana. And today we are going to be talking about the first example from Larson's 9th edition, section 9.9, representation of functions by power series. And the main focus here is dealing with the very commonly known geometric power series. For example, let's consider the function f of x equals 1 over 1 minus x. And let's say that we wanted to find a power series for that. Well, there are a variety of ways in which this can be done, one of which is to take several derivatives and use a sort of Maclaurin polynomial expansion. And in this case, Maclaurin would be what we would be looking for, since it does say that the representation here would be centered at 0. And of course, you would then evaluate each of those derivatives at 0, including the original f of x, and then sort of step back as you piece it together into its polynomial form, and then look for a nice formula representation of that. And all the while you do this, the outcome will look a little bit like this, the very popular geometric power series that you've probably worked with already. And that's really what it's all about. It's manipulating the original function so that it takes on this a over 1 minus r appearance. And then once you've done that, to find the interval of convergence, it's going to be very simple, because then you can avoid the ratio test and just use the geometric definition of convergence, absolute value of r less than 1. So let's go ahead and take a look at our first example here in a couple of slides over. We're considering the function f of x as 4 over x plus 2. We will be centered at 0. And we want to remember at the very end to indeed state the interval of convergence in this particular case. So I'm going to rewrite here very briefly that power series representation, or the geometric series, and what its sort of formula, if you will, would be if we were to add all those terms up. And we'll also consider where that particular power series will be convergent. So what it boils down to for your original function f of x, 4 over x plus 2, is we need to get this guy to look very, very similar to this guy. Do whatever it takes within the bounds of mathematics to make these two look similar. Well, the very first thing that one could do is think, well, obviously we have different variables, r instead of x. I wouldn't worry about that. That's always going to happen, because most often your function representation will be in terms of x. Just pretend that's an r and you'll be fine. We do notice that we would prefer a different order here, so we could just swap them via the commutative property. And then we notice that there's still some issues that we need to address. For example, in the geometric summation formula here, we have a 1 in the denominator that leads things off. Down here, we do not have a 1, we have a 2, but that's going to be a pretty easy fix. If we would divide the numerator and the denominator by 2, we would come to this result, 2 over 1 plus x plus 2. So we've taken care of the 1. Next, you'll notice that with all geometric representations, you do need to achieve this minus sign in the middle. We do not have that at this particular case. But once again, a pretty easy manipulation will take care of that. Change that plus to a minus. Just make sure that you offset that change by making your quantity x over 2 a negative. And now you'll see that you've got exactly what you bargained for. You have got yourself a very easy geometric representation here, where the a value, that would be what is in the numerator, would be, 2, and the r value would be the quantity here in the parentheses, negative x over 2. You don't want to forget that negative sign. It's going to be very important. So when it comes time to write your final answer, what is the power series? Well, it's just this summation expression. As n goes from 0 to infinity, except we do have our value of a, which goes by the name of 2 now, and our r, negative x over 2, all raised to that nth power. And that would take care of the first part. of the question. The second part asks us to find the interval of convergence. Well, once again, you're just going to deal with this particular formula that we've got written down here. You'll say that the absolute value of negative x over 2 is going to be strictly less than 1. Now, to take care of the rest of this, you'll just simply rewrite it as a compound inequality. And then we will slowly get this x value by itself. I'll multiply all three sides by a 2. And then to get rid of the negative sign, we would just divide or multiply all three sides by -1, which obviously is just going to change the sign of every term, but it's also going to do something else. If you recall, whenever you multiply through an inequality by a negative, you will change or reverse the direction of the inequality signs. And that's important because had you not done that, this inequality would make very little sense anyway. So you could then just sort of flip all of this around or view it in a mirror, and it would read -2 is less than x is less than 2. Basically, you're saying that your values are between -2 and 2 exclusively. That means you're not going to include the -2 and 2, and that comes from the fact that this inequality symbol up here is a strictly less than. A lot of students think that you still have to go through the process of checking the endpoints, just as you would if you were, say, performing the ratio test on this particular problem. But that's not necessary because the geometric representation here of the convergence says it is strictly less than. And I'll invite you to try plugging into a -2 in for this power series and just find that that is going to be the case, that you will not converge at the endpoints. Before I end here, I would like to address a potential third method of finding this power series. Now, if you recall, obviously we have this method that I just showed you. You could expand this with a Maclaurin polynomial technique. That would take quite a bit of time. Several derivatives might have to be taken before you feel comfortable with determining what the formula would be. But another interesting and less calculus-like method would just be a long division process. Taking the 4 and dividing it by 2 plus x. Notice I switched the order of the x and the 2. It does make this work a little bit better. And essentially what you would do is begin the process of the division by saying 2 times what would be 4? Well, of course, that would be 2. And you would go ahead and multiply your 2 and your 2 plus x, and then do the subtraction, etc. And you'll notice that this will go on forever and ever. I'm not going to finish it, but I would invite you to continue to do a few more steps of this, and you'll see that the term-by-term representation of this will match exactly the term-by-term representation had we decided to run several n's starting with 0 in for this particular power series. So it's just another neat approach to some of the calculus that you've been doing. Anyway, I hope this helps. You can check out some of my other videos on Larson's 9th edition, Chapter 9, and perhaps get some more help with the geometric representations. Thanks for watching, and I'll see you next time.